Welcome to the second part of this PID controller lecture. Please recall that we have already studied on-off and proportional controller. On-off controller is a very simple controller we have seen. However, the output of this on-off controller is a oscillatory output. Okay, that means the output of a system, suppose this is our desired output level, that means 10. So then if I employ a on-off controller, then the output will ultimately fluctuating and never settle down to a steady state. So that means steady state error is never possible to become zero. So that is the major problem with this on-off controller. However, in case of proportional controller, we have seen if I use a KP controller, then error is there initially, but if we increase the value of KP, then somehow we can manage this error more. We can reduce this error. But again, there are two major problems with this KP. One is steady state error can be minimized but cannot be reduced to zero. Okay, and if we increase the KP further, then it will create very high oscillations, but ultimately some error is still be there. So overshoot will occur if you increase the KP value more and more. So these two are the basic problem with this KP proportional constant. So what are the solutions? The solutions are two. If you ignore the error part, that means maybe we can tolerate some error, then but we cannot tolerate any disturbances or we cannot tolerate any overshoot, then we should employ, along with a proportional controller, a derivative controller. A derivative controller has power to minimize the overshoot, but it do not alter any error. So that means, let me show you with this diagram. Suppose this is again a desired value, let's say 10. If you, in case of Kp equal to a very high value, let's say Kp equal to 20, we are getting very high oscillations, and the error is like this. Error is, let's say, 0.05. Okay, or 0 or 5% error is there. Instead of Kp, if you use Kp plus Kd, that means proportional plus derivative control, then the oscillations will not be there. Oscillations will be very less, but error will be again 5%. So you understand, I guess. So D controller reduces the oscillations. However, it cannot reduce the error. Vice versa, in case of PI controller introduces more oscillations, okay, but it actually makes error zero, exactly zero. So if you use P controller along with I controller, ultimately it should looks like this one. So maybe oscillations will be high, but ultimately it will match with the desired value. Okay, so which one is better solution? It definitely depends on the applications. If we tolerate some amount of error, then we can go for PD controller, but if we cannot tolerate any error, that means error should be always zero, exactly to be zero, then we should employ PI controller. Okay, so in next few slides we will study first PD controller, PI controller, how they can be realized, and then eventually we will start PID controller. So as I have said that in PD controller, the actuating signal is basically, it is not only proportional to the error signal only, it is also proportional to the derivative of the error signal. Let me explain it with the mathematical expression. So this is how this is the error, I mean actuating signal. It is proportional not only to the error signal but the derivative of the error signal also. So we can easily write the equation number 2 by introducing a new constant called derivative constant kd. Okay, and we can also, after taking Laplace transformation, we can write down the equation number 3, and you can see easily we can realize this equation 3 because AS signal is the sum of these two signal. So AS signal is sum of Kp into S plus SKD into S. So this is how it looks like. And so what are the major advantage or I mean pros of this PD controller? As I said, in D controller, let me illustrate here again. So this is, let's say, the I mean desired value 10, and in case of Kp, normal Kp, I mean normal Kp means Kp equal to proportional controller Kp equal to 1, then this will be the output. In case of higher Kp, more oscillations will be there, but ultimately some error will be there. Okay, steady state error cannot be 0. But in case of Kd, the problem is solved. The oscillations is no more, but the error is still being some 5% or 10% error will be there. So what are the pros? Pros is it reduces the maximum overshoot that is written over here, and con is cannot reduce the steady state error. Okay. Similar to PD controller, in PI controller, the actuating signal is proportional to the error and the integral of this error. Okay, so we can easily write the equation number 2 as mentioned here, and after Laplace transformation, we can write down the AS formula. And the realization is again very simple, not very complicated. The error AS signal is summation of two signal, again Kp into S plus Ki by S into Es. Similar to the PD controller, but PI controller here, the main advantage of this PI controller is it can reduce a steady state error to exactly 0. However, it introduces some oscillations. So that means for illustration purpose, we can say if I use a PI controller, oscillations may be higher, but ultimately it will follow the exact reference path. So if we can tolerate this kind of oscillations, but then we can employ this PI controller over here. Okay, so because the advantage is error should be exactly to 0. That is the major advantage of PI controller. The rest advantage and disadvantage, just for sake of completeness, just read at once. Okay. So finally, we are here at to study PID controller, and as the name suggests, so here the actuating signal or AT is the addition of, it is proportional to the error signal as well as the integral of the error signal and derivative of the error signal. Okay, so it is the combination of all the effects of proportional, integral and derivative. Now from equation 1 we can easily write equation number 2 followed by equation number 3 and see the realization. It is perfectly simple. That means AS is now this summation of three signals. One is Kp into S plus KDS into S plus Ki by S into Es. Okay, so this is the simple realization. Please note that here the on the left side of the Es, there is a comparator, and on the right hand side of this controller is connected to final control element or plant, that you please imagine. So this is the inside the controller box. So designing a controller means you need to find out the value of Kd, Kp and Ki. Okay, so as a control engineer, our job is to find out Kp, Ki, Kd value so that the output meets the desired specifications. Let me show you one example. Here you can easily see that the first one, I mean KP controller is used, I mean proportional controller, because the other terms are 0 here. So only P controller, in case of 4, KP value equal to 4, this is the output. This is the output. So error, huge error is present here. But in case of second one, the yellow line, it is a PI controller basically, because D part is 0, so PI controller. So since it is a integral controller, that means I am expecting error should be 0. And yes, you can see oscillations is very high. I mean maximum overshoot is high because integral control introduces oscillations. So oscillations is high, but error is ultimately eventually 0. Similarly, last one, the pink one, it is a PID controller output, which gives me the almost perfect output. That means no, overshoot, very high overshoot is reduced, but error is also, almost negligible. Okay, so this is the power of this PID controller. So let me start the pros and cons. Of this PID controller. The pros is it is again the greater accuracy, the algorithm is more energy efficient and easy solutions, of course, and the most important thing is it can be implements as an analog, digital, mechanical, pneumatic form of solutions. That means in electrical PID controller we can generate, you can generate mechanical PID controller and anything. So that's why PID controllers are more popular. However, there are certain disadvantages also, like it is especially suitable for MIMO systems and linear systems. It is not applicable for non-linear systems. So with this is the theory of PID controller.